My research involved predicting the presence of heart disease using the k-nearest neighbor classification, logistic regression, and feed-forward neural networks. This is by Rebecca Xiong and my mentor, Dr. Xiaonan Zhu. So, as an introduction, why is it important to predict the presence of heart disease? Well, heart disease remains a prevalent and formidable global health challenge, accounting for a significant number of mortalities worldwide. Timely and accurate detection of heart disease is crucial for effective management and intervention, potentially mitigating its adverse impact on patients' health. Additionally, previous studies have demonstrated the potential of machine learning models in medical diagnostics. For example, a Mary 2020 in the Journal of Biomedical Physics and Engineering found that there is a high potential for deep learning to assist dermatologists in the detection of skin cancer, including melanoma and non-melanoma malignancies. The specific research problem addressed in the study is to ascertain the accuracy and efficacy of these three machine learning algorithms in predicting heart disease, and by comparing their performance on a comprehensive dataset provided by UC Irvine containing relevant medical features and heart disease labels. This research seeks to identify the algorithm that offers the highest predictive accuracy, thus potentially serving as a valuable decision support tool for medical professionals. And to provide background to the approach, it is essential to understand how these three machine learning techniques work. So first, k-nearest neighbor. K-nearest neighbor belongs to a subcategory of non-parametric models that is described as instance-based learning. So models based on instance-based learning are characterized by memorizing the training dataset. And this algorithm operates based on the principle of similarity, where a new data point is classified based on the class labels of its k-nearest neighbors in the training data. So the class of the majority of the k-nearest neighbors determine the predicted class for the new data point. For example, in this graph, if I were to classify this data point, and let's say I wanted to look at its three nearest neighbors, well, it'd be this one, and this one. And based off of that, it would classify it as one, as you see in the graph. Next, there's logistic regression. So this is a binary classification algorithm that estimates the probability of a data point belonging to a particular class using a logistic function. And it models the relationship between the input features and the binary outcome, providing a probabilistic interpretation. So this here is the equation for the logistic regression, where Z is the net input, the linear combination of weights, and the inputs. That is, the features associated with the training examples. Next is the feed-forward neural network, which is a type of artificial neural network which consists of input, hidden, and output layers of nodes connected by weighted edges. Typically, training a feed-forward neural network involves the following four components: layers, input data, and corresponding output, loss function, and an optimizer. For example, if I look at this graph here with four hidden layers, an input layer and an output layer, I could represent this using this function, where F1 is the function connecting the input layer to the first hidden layer, and F5 connects the fourth hidden layer to the output layer. And these functions F can be represented by this equation, where WH is the weights, CH the biases, and CH the activation function. The output from a previous layer is utilized as the input for the next layer to formulate such multi-layer networks. In the feed-forward neural network, this function, where the parameter phi is therefore a stack of all weights and biases, where the weights and the biases are, in this instance, anything in the set of 1, 2, 3, 4, and 5. So basically, this model processes input data through multiple layers of nonlinear transformations, finally generating an output that represents the predicted class probabilities. So the method. Each machine learning algorithm was coded using Python. So in each method, we first imported all the proper libraries for the algorithm. Then there was data preprocessing. So the data set from the machine learning UC Irvine Machine Learning Repository includes 303 instances and 13 attributes, where the target field refers to the presence of heart disease in the patient. And the dataset distinguished presence using the values 1, 2, 3, 4 from absence, which was represented by the value of 0. So as part of pre-processing the data for all the machine learning methods, the following code was used to remove any rows that contained one or more missing values, so these first two bullets. And additionally, the target field was converted to binary values, which is represented by this here. So the value was set to 1 if it was greater than 0, and set to 0 otherwise. Then there is data analysis and classification. So this included splitting the data, training the data, and then scaling the features using standard scalar. And lastly, there is the implementation of the models analyzing each algorithm's accuracy. So first, k-nearest neighbor. So these first two lines fit and evaluate the model, and then this made the prediction. Then these lines of code identify the best value of k. So it used a for loop to go through each range of k and then finally evaluate the best one. And then this was used to evaluate the accuracy of the best k identified from that for loop. Next was the logistic regression. So this first line instantiated the model using the default parameters, and then this fit the model with the data. Then these lines of code just visualize the accuracy in a confusion matrix, which I'll show later in the results section. Next, there is the feed-forward neural network. So in this one, I created a model with 3 layers, which you can see represented by these lines. And then I compiled the model and specified the loss function, the optimizer, and evaluation metrics to be used during the training. Then this fit the model on the dataset, and then these evaluated and visualized the model. And then down here, this evaluated the accuracy of both the training and the test set. So the results. Ultimately, the feed-forward neural network had the highest accuracy at 88.33%. And the k-nearest neighbor had an accuracy of 83%, you can see here. And the classification report includes precision recall, F1 score, and support. So basically, precision is a measure of how accurate the positive predictions of the made by the model are. So basically, out of all the instances predicted as positive, how many are actually positive? High precision indicates that the model has a low rate of false positives, meaning that when it predicts a positive outcome, it is usually correct. Recall measures the ability of the model to identify all positive instances, answering the question of, out of all positive instances, how many were correctly predicted as positive? High recall indicates that the model is good at capturing a large portion of the positive instances. Then the F1 score is a balance between precision and recall, and it is the harmonic mean of precision and recall and provides a single metric that considers both false positives and false negatives. And the F1 score is useful when you want to find a balance between precision and recall, especially when class distribution is imbalanced. And support in a classification report indicates the number of instances in each class, and it tells you how many actual occurrences of that class were present in the data set. So here in this precision report, you can see that this had an 83% accuracy and a 60 on support. Then with the logistic regression, you can see its classification report here, and it had a slightly higher accuracy than K nearest neighbor at 85%. And here you can see the confusion matrix. So basically, here this correctly predicted the presence of it correctly predicted the presence of heart disease in 22 patients, in the absence of heart disease in 29 patients. And then the feed-forward neural network had an accuracy of 88.33% on the test set and an accuracy of 99.16 on the training set. And so this is a visualization of the training accuracy and training loss as the epoch number increases and the classification of the results. So conclusion. The feed forward after training, testing, cross-validation, and comparison, this study identified that the feed-forward neural network was the most accurate for this dataset at 88.33%. And future research holds promise in exploring the potential of supervised machine learning and deep learning models. And further improvements to the study include tuning the parameters of the feed-forward neural network and using other models such as support vector machine, decision tree, and more. Thank you.